A'udhu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. This is my lecture about the topic of properties of nanomaterials. As we discussed in the earlier lectures, that it will be a series of lecture regarding the nanomaterials and its property. And this course is from the course outline of nanophysics and technology, having the course code of PHY445. Actually, for research purposes or investigating materials, we have two basic approach. One is the top to bottom approach, and other is the bottom to top approach. In the top to bottom approach, we slowly increase the magnification of the tool with which we want to observe the materials, and we are trying to observe the materials till at very high resolution. It is not very easy, but the development will perform using various tools, including scanning electron microscope, transmission electron microscope, atomic force microscopic, and some other new discoveries. And in the bottom to top approach, atoms are combined together in simulation, and the unit cell is converted into supercell, which is simulated in the systems, and then the properties are predicted. So these are two different approaches for studying the materials. So if we see and observe the size of the materials at different scales, at different materials, so we can get more information from this scales. Here in the horizontal scale we have the particle size, and on the vertical different sort of the materials are shown. If we see the human ear, then the human ear comes in the range of 100 to 10 to 150 micrometers. Similarly, the pollen comes in the regions of 10 to 100 micrometers. If we see the bacteria comes in the range of 0.1 to 10 micrometer size, and the soot, it comes in 0.01 to 1 micrometer size. And similarly, we have hepatitis B virus. This comes in around 0.01 to 0.02 micrometers, and the carbon blacks is coming in the range of 0.001 to 0.1 micrometer size. So conventionally, material have grain size anywhere from 100 micrometer to 1 millimeter, and more particles with the size between 1 to 100 nanometer are normally regarded as nanomaterials. So the average size of an atom is of the order of 1 to 2 angstrom. 1 nanometer is equal to 10 angstrom, or 1 angstrom is equal to 10 to the power minus 9 nanometer. So this is a relationship between angstrom and nanometers. So normally in 1 nanometer there are 3 to 5 atoms. So two principal factors cause the property of the nanomaterial to differ significantly from bulk material. The theme of the lecture is to investigate why the properties of materials are different at nano size and from the properties of the material at bulk size, and what is the reason for that, justification for that. So two of the reasons for this, that the property of nanomaterial are different, of the same material are different from the bulk material, is that the nanomaterial have increased relative surface area and the quantum effect. When we are coming toward the lower size of the particles, the quantum effect occurs. So these factors can change or enhance the properties such as reactivity, strength, and electrical characteristics. So we want to discuss one of the the surface effect in detail. So In the surface effect, when the particle size decreases, a greater proportion of atoms are found at the surface compared to those inside. So for example, a particle of size to around 30 nanometer, so in it around 5% of its atom is present at the surface. So if we are coming toward the lower size particle material, so it's where the size is around 10 nanometer, so it's around 20% of its atom is on its surface. In the case of 3 nanometer size particles, 50% of atoms are at the surface. So nanoparticles are more reactive than large particle because the number of surface atoms drastically increases. If we see from going from size 30 nanometer towards size 3 nanometer, the surface atoms percentage increases from 5% to 50%. So the other is the quantum effect. Another reason for the improved property is the quantum effect, and that is one is the quantum confinement. And the quantum confinement, it can be observed that when the diameter of a particle is of the same magnitude as the wavelength of the electron wave function, then the quantum confinement is responsible for the increase of energy difference between the energy state and the band gap. So this similar phenomena tightly is related with the optical and electronic properties of semiconductors. So when the materials are in small level or a small scale, nanomaterials, so their electronic and optical properties differ from its bulk property, and definitely its electronic and optical properties are improved compared to the bulk properties. So how we can classify nanomaterials in different categories? So nanomaterials are those which have structure components with at least one dimension less than 100 nanometer. So the first one is the one dimension in nanoscale. That are actually the thin films, surface coatings and computer chips, and the other is the two-dimensional in nanoscale, which are nanowires and nanotubes, and the third one is the three-dimensional in nanoscale, that are nanoparticle, precipitates, colloids and quantum dots. So we can discuss one of the example of the nanoparticle is the carbon black, and investigate its property and structures, and we also need to develop the relationship between the structure and property of this material. So as we already know that by changing the structure of material, the property greatly changes. So playing with the structure of the material can improve the properties of the material as well. So we can consider the graphite, which is actually the crystalline form of carbon. So the graphite is actually in atoms are covalently bonded. A single atom is covalently bonded. A single carbon is covalently bonded to 3 carbon atoms, and it gives trigonal geometry. In this case, the bond angle is 120 degree, and carbon atom in graphite is sp2 hybridized. So 3 out of 4 valence electron of each atoms are used in bond formation with other carbon atoms, while the 4th electron is free to move in the structure of graphite. So how we can develop the structure of graphite? If you see, it has basic trigonal unit that are united with each other and giving its hexagonal rings. See, in the lower scale we have 6 atoms present at the corner, and that is so in this hexagonal structure there is a ring of carbon-carbon bond, and its length, the bond length between carbon-carbon is equal to 1.42 angstrom. So in graphite, these rings are form flat layers, and these layers are arranged in parallel one above each other, forming the hexagonal structure. So the layer are 3.3 angstroms apart from each other, and there are some forces which are holding these layers together. So these layers can slide over one another and it is in reality is very soft. So actually the fourth electron of each carbon atom form delocalized p bond with this, which spread uniformly over all carbon atoms, and due to this reason graphite conducts electricity parallel to its plane. So this graphite, that this is normally used in as a solid lubricant and moderated in nuclear reactors and electrodes for pencils. The other form of carbon is the fluorines. So that has been developed in 1996, and some scientists got Nobel Prize on this. So in 1995 they have developed, this is one of the allotropic form of carbon. It was discovered that this is one of the allotropic form of carbon, and in this regarding this structure, it was considered that the atoms in these structures are arranged in closed shells. So these new forms were found to have structure of truncated icosahedron and was named as a Buckminster fluorines after the name of a scientist who designed these ideas. And later on in 1990 some scientists, Kretschmer and de Hoffman, for the first time isolated the C60 fluorines, and they were successful with the help of some isolable quantity of C60 by causing an arc between two graphite rods to burn in helium atmosphere and extracting the carbon condensate. So this is some introduction about fluorines. So its applications are, its structure is hexagon, 20 hexagon and 20 pentagon. So we have this application in numerous field of life. This so because of its interesting properties, it has numerous applications. So fluorines have synthetic, pharmaceutical and industry applications. So some diseases like degenerative diseases and ordinary aging process are caused by intracellular oxygen free radicals with unpaired electron. So this is 60 fluorines can react with radicals and thus halting the process of aging. So this is one of the application of this. So it's a good MRI contrast agent, and that can be used in light emitting diode as well. So this is vastly used in different electronic equipment and computer devices. So the other, the carbon nanotube electropic forms are the one of the different and interesting structures of the carbon is the carbon nanotubes, and these are actually the cylindrical nanostructures, and these nanotubes have been constructed with long length to diameter ratio of, and this is actually significantly larger than for any materials. Its properties are also very interesting because of its unique structures. So the cylindrical carbon molecules have unusual property which are valuable for nanotechnology, electronics, optics and other fields of material science and technology. So due to this material have actually extraordinary thermal conductivity and mechanical and electrical properties. So it's widely used in different aspects of life, especially where we need a material which have with high conductivity, thermal conductivity. And this is, so this carbon nanotube is strongly recommended due to various structural materials because of its high strength. Such nanotubes are a member of the fluorine structural family because it's which also includes the spherical buckyballs, and the ends of a nanotube may be kept with a hemisphere of the buckyball structure. So their name is derived from their long hollow structure with the walls formed by one atom 6 sheets of carbon called as graphene. So these sheets are rolled at a specific and discrete angles, and the combination of the rolling angle and radius decides the nanotubes property. For example, whether the individual nanotube shell is a metal or semiconductor. Nanotubes are categorized as a single wall nanotube or multi-wall, maybe in some cases as multi-wall nanotubes. So individual nanotubes naturally align themselves into groups held together by van der Waals forces. So the properties and application of nanotubes. Nanotubes have structure have very interesting property, and that is why it has wide range of applications, because the nanotubes are extremely strong and stiff and relatively ductile. In some cases, when we are dealing with material, when we improve the mechanical property of the material, then it loses ductility. So this is one of the problem with the materials. Increasing the strength of the material, we can lose the ductility. So what happen if we consider these carbon nanotubes? So it's a very interesting property, because at the same time it's strong and it's also strong and stiff and relatively ductile. So for single wall nanotubes, tensile strength is range between 50 to 200 gigapascal, that is more than carbon fibers. So this is the strongest known materials. So elastic modulus values are of the order of 1 terapascal, with fracture strengths between 5 to 20%, and they have very low densities. So because of these properties, because of these very interesting properties, the carbon nanotubes have been termed as the ultimate fibers. So it has been regarded as 100 times stronger than steel, at the same time 6 times lighter. So it have both two very interesting properties, because at the same time it is very stronger and it is also very lighter. For aviation and for aeroplanes and for the space technology, we are often interested to search for material that are stronger, that have high strength, ductile in some through some sense, and are lighter in weight. But in normal cases, when some materials are lighter, so it's not very hard, and it's not very strong. So there is some compromise between the strength of the material and its ductility and its weight. But we can get interesting properties of such material from the carbon nanotube, where it is very strong and even 100 times stronger than steel, and at the same time it is lighter in weight than steel. So it's really interesting for the technology. So you can also find applications in the composite materials. So the same material can be act as either conductor or insulator depending on their structure as generality. So they find their application in molecular, electronic and computers. They are used as an ultra sensitive electrochemical sensor. And one of the other interesting properties that we can also use the same material as a conductor or semiconductor, depending. We can change this conductivity from the different levels, and that is very interesting, because it's in application of electronic industries. And we can use this in microelectronics, or maybe in computers that are ultra sensitive, and especially we can use it in sensitive electrochemical sensors. The other applications of these carbon nanotubes are in battery and fuel cells. So field emission results from the tunneling of electron from a metal tip into vacuum under application of strong electric field. So such diameter, so we have small diameter and high aspect ratio that have longer carbon nanotube is needed to compare with the conductivity. So the small diameters and high aspect ratio, that is actually lower loading of the carbon nanotube, is needed to compare to other conductivity additives to achieve small electrical to achieve same electrical conductivity. So this is some really interesting application of the carbon nanotube, which make it interesting for us and that have wide range of applications. So we have carbon nanotubes that are very favorable for field emissions, and even can for moderate voltages and strong electrical develops at free support of the carbon nanotube. So it's a large surface area and high absorbency of carbon nanotube make it ideal candidate for use in air gas and water filtration. So some of the nanowires and its application of the nanowires are the that a nanowire has nanostructures, and this is one of the structure of the nanowires. Here in this case we can see that the nanowires are arranged in a very regular patterns, and these nanowires have very interesting applications. So its diameter of the nanowires is around 10⁻⁹ meters. So alternatively, nanowires are defined as the structure to have a thickness or a diameter constrained to tens of nanometer or less, and an unconstrained length. So at this scale, quantum mechanical effects are important, which coin to the term of quantum mechanical wires. The other nanowires are arranged in this order. It's very interesting. An array of silicon nanowires. So we have different types of nanowires that exist for different materials, especially the metallic, just like nickel and platinum and gold. So in case of semiconductor, we have nanowires are also nanowire morphology is also found, that is for silicon, indium nitride, and gallium nitride, and etc. Similarly for some insulating materials, just like TiO2 and SiO2 as well. So these molecular nanowires are composed of repeating molecular units in case it may be organic or inorganic. So the nanowire could be used in near future to link tiny component into extremely small circuit using technology. So such component could be created out of chemical compound. So the typical nanowires exhibit aspect ratio, that is actually the length to width ratio of 100 or more, of 1000 or more. So in such cases, this is also called as a one-dimensional materials. So the nanowires has been many interesting properties, and these properties are not actually found in the bulk of the materials. So this is because electron in nanowires are quantum confined laterally, and thus occupy energy levels that are different from the traditional continuum of energy levels or bands found in bulk materials. So these interesting nanowires are synthesized in laboratory from elements. So there are many applications where nanowires may become important in electronics, optoelectronics, and nano electromechanical devices. So this is something about the nanowires and its applications. So I hope we can discuss some new topic in the upcoming lectures. Thank you very much.